Right. So I think Nigel Moriarty had his hand up first. So.
Yeah, thanks, John. I noticed that, and this is one of the topics I was going to talk about in my talk, is that you don't do minimizations, you only seem to do scans. Is that because when you do a minimization, bigger molecules, in my experience, seem to bend around and hydrogen bond to themselves, which is in most cases not a real minimum?
Let me make sure I understand your question. WebMO certainly supports geometry optimizations. That's,
Yeah,
I assume, what you mean by minimization. One can choose what type of calculation one wants to do.
Yeah.
And let me also address that when one does a coordinate scan using WebMO, set up with WebMO, but using an engine. Let's be clear, you know, which role, what program does which task. One can, if it's supported, set up relaxed scans, rigid scans, or in fact combinations of the two. So you can fix some coordinates and relax other coordinates, and so that sometimes is useful during a scan. I'm not sure if I've actually addressed your question. I wanted to make sure that I understood it and represented what WebMO can do. Would you like to follow up, Nigel?
Yeah, I mean, I'm just saying that your demonstrations didn't have that problem. And it's a problem that I've seen, is that in a long molecule, it will sometimes bend around and you have this hydrogen bond between the two ends, which is clearly not a physical, thing. It's actually not directed specifically at you. It's a more general question, which I was hoping to discuss perhaps after my talk, which is last.
Right. Oh, well, that's a good point. That would be sort of more how one sets up the calculation. And, you know, I mean, one way perhaps of doing that is to, let's say, fix a couple bonds in the middle that would prevent it from doing that. But in a highly flexible molecule, one might find that. You know, so another possibility is make sure one starts in a good starting position so that you don't end up over there. And again, that depends on the algorithm used by the underlying engine. Will it fall to the nearest minimum, or is it some other type of algorithm that knows how to look further? So good point. I look forward to your talk, and then we can discuss it perhaps further.
Thank you.
Okay. I had some comments about that, but I want to let Nigel Richards ask his question first. Just to
well, you should comment, but
oh, okay. I mean, I can briefly. So yeah, I mean, the default behavior of MOPAC is to do geometry relaxation. So that's kind of the native behavior. You know, if you don't say anything else, that's what it'll try to do. And yes, kind of generically, floppy molecules can attach to themselves, and that's preferred by dispersion forces. Ideally, it's solvation and just sampling conformations that kind of prevents that from being a dominant part of the configuration space. And I guess I don't have enough experience with the solvation models to know if they do successfully suppress like long linear molecules from wrapping around and connecting to themselves. Ideally, they should, if an implicit solvent model like Cosmo is really representing the physics of solvation. But I'm not actually clear if that is successful all of the time.
If it's a long N alkane, then because it's hydrophobic, if you do solvation, it'll fold on itself.
Oh, it will. So it doesn't necessarily prevent that, because ideally, like, there should be some solvents where it does stay unwrapped, and then maybe others where it wraps.
Yes. If it's hydrophilic, then it'll probably stay linear.
Right, but the current implicit solvent models can't really give you much of a detailed description of the solvents beyond their.
Oh, sorry. If the polymer that you're working with, if the long chain is hydrophilic, then it will lose the incentive to fold.
Yeah, but for example, like there's not a really strong distinction between a polar and non-polar solvent in the Cosmo solvation model. Like
that's right. It's
not really capturing a rich enough set of physics to necessarily describe those differing behaviors.
Oh, that would explain what I'm seeing.
Yeah. Anyways, maybe on to the next question from Nigel Richards.
Yeah, so I want to keep it general as well because we're in the kind of group time here. But
Yeah, I'm trying to kind of just expand this
right.
out.
But so I make two comments. The first is I'm delighted to see the resurgence of Zindo. It's absolutely the best way of getting metal spectra and transition metal spectra anyway. And I guess that leads me to the point, right? One of the weaknesses of, oh, well, maybe I've got this wrong. Maybe it's no longer a weakness, but traditionally one of the weaknesses of MOPAC has been the inability to treat transition metals in different oxidation states and spin states. Certainly for the, first row, iron, nickel, cobalt, copper. And I would certainly advocate anybody who's developing, I'm not qualified, I really would like to see metals. I mean, it seems to me that one of the problems that semi-empirical theory has is that DFT has been so successful in describing the molecular geometries of organic molecules. And it can, in principle, do metals as well, although of course it can't because it doesn't handle 2 electron properties properly, although nobody seems to understand that. I kind of worry that semi-empirical methods are being essentially ignored because of the success of DFT. And I wondered if Jimmy or somebody can do some education for the students here as to the advantages of semi-empirical over DFT, or semi-empirical as implemented in the neglected differential overlap in MOPAC. If somebody could make some comments about that, because people have forgotten fundamental theory and they don't really understand that DFT has massive limitations.
Yeah, any.
That's not a question, but that's a chance for Jimmy to comment about the advantages.
Okay, yeah, I mean, I let Jimmy speak about that.
Well, actually, I would like to defer to Will, as he has more experience in working with students. Will?
Let's see, I'm not quite sure. You mean in comparing DFT to semi-empirical? Yeah, I'm not sure if I can sort of make a comment on that. I mean, I at a very, very coarse level, or oversimplified level, I should say, I point out that semi-empirical is so fast because it's simpler theory, just less mechanics, machinery to go through, and that it is also relatively accurate because it's parameterized based on experiment. But I do point out that with any kind of parameterization, its accuracy is sort of limited roughly to the training set, if you will. And so that's how I differentiate between, let's say, semi-empirical and then the full ab initio methods. Between this is more for the sake of students, not for the experts who are already aware of this. Between DFT and let's say, what do you want to call it, non-DFT methods, the difference is that there is a sort of systematic way of improving the accuracy of the sort of or typical orbital-based methods to higher accuracy as one expands the Hamiltonian and the wave functions respectively. And so that's great, except of course there are scaling challenges that one encounters. And DFT though builds in some of the correlation just up front, but it's a little bit of black magic in terms of what density functional is being used. And so there's not necessarily a way in which one can systematically improve and see whether or not one's results have converged using DFT. That's my undergraduate level description to students, kind of comparing those approaches. But I think Nigel was getting at something a little more fundamental. And of course, I would enjoy hearing your perspectives on the role of semi-empirical. I mean, So I'll leave it at that.
Well, I mean, I mean, there are some fundamental limitations of density functional theory to do with it, self-energy of electrons and this and that, and the fact that the energies of the unoccupied orbitals have no meaning because there's no density in them. But you know, but these issues are never emphasized, and it seems to me that the semi-empirical community needs to somehow get the message out that DFT is not the answer. I mean, everywhere I look, AI is generating new functionals, and this is the in thing right now, and DFT is everything. But there are just some as you point out, some fundamental difficulties with DFT. And it seems to me that semi-empirical is regarded as a dinosaur technique, which clearly, well, it obviously isn't. But I just don't know how we get the message out.
Yeah,
I'll defer to yeah.
Yeah, I have a point to this discussion as well. Like working with larger systems, some of the errors of DFT, which are quite small in small molecules, become much more obvious. And we are running across this a lot in the biomolecules. It's the electron delocalization error, which causes the charge leak from one side to some other side with orbitals with similar energy. And of course, it is negligible in small, well-behaved neutral molecules, but in a protein where there are multiple charge amino acids, this become an issue. And in fact, we run across cases where the DFT calculations, much more expensive, were yielded worse results than the simple semi-empirical calculation, which in case of the MNDO-based method is not prone to these errors. It also makes a difference between this kind of semi-empirical methods and DFTB or XTB, which also suffers from the DFT derived errors. We have shown it in one paper where we looked at this, but it's something that is going against the mainstream, and it would be hard to push it as the main message.
Yeah, I mean, I have been interested in working with MOPAC precisely because I think that semi-empirical modeling can have greater future impact, and that the investment in it has been, there has been an underinvestment in trying to build better models. Like DFT captured the popular imagination in the theoretical community in the late 80s, 90s, and since then. And it's just so much more development has gone into that, and it's benefited from that. And semi-empirical modeling has had fewer investments. There's been the DFTB community that has its own group of developers. XTB was an effort, kind of that's an offshoot, I think, of DFTB in some sense, from Professor Stefan Grimme's group. There was an isolated effort at the Naval Research Laboratories in the late 90s. I think I just disconnected again. Can people hear me? No, okay.
Yeah, it works.
Okay, because I've already been disconnected once. Yeah, I don't know. I see opportunities, and especially like, so the cases you're bringing up, these are cases where there are distinct qualitative problems with DFT based on semi-local functionals that completely ignore Fock exchange, that even crude calculations that contain Fock exchange will avoid those types of problems, like the electron delocalization errors. Those are qualitative problems that simply don't exist when Fock exchange is present in a calculation. But on like the physics side of things, people tend to avoid using Fock exchange because of the great cost in like plane wave based codes. But then when you're kind of comparing more similar models like B3-LIP, which has Fock exchange, with semi-empirical models, like just because of more effort that has gone into density functional theory and fewer sources of error, like basis set convergence, when both are working qualitatively roughly well, there are advantages to the more expensive things. Like there is this cost accuracy trade-off. Now, I think there are opportunities for semi-empirical models to compete better and offer, better cost accuracy trade-offs in the future, but just more work needs to go into that. And in particular, like one of the, I didn't mention this in my talk, this is a good place to bring it up. My personal research interest is in methodology interest and things that are a bit more exotic than semi-empirical models. But one thing I showed was that there's certain higher levels of theory, like certain electron correlation models that bring in new physics that have fast algorithms that scale extremely poorly with the size of a basis. So in ab initio calculations, their cost is extremely large, and the added cost to just a normal DFT calculation would be enormous. But at the semi-empirical level, because you're using minimal basis sets, they're able to bring in new types of physics, like a more accurate description of dispersion. These are like random phase approximation methods, where the cost prefactors change such that it would increase the cost of a semi-empirical calculation by maybe like 5 times. And so for 5 times the cost of a very cheap thing, you're potentially building in physics that is extremely expensive to access in larger basis. So that's where I think some of the new opportunities lie, in taking higher levels of theory that are greatly penalized by increasing basis set sizes and giving people access to those levels of theory with parameterization that tries to overcome the shortcomings of operating in a smaller basis set. So that's been something I've been pushing for. And I have written several grant proposals related to that, and they have all been rejected so far. So I would like the opportunity to explore that, but it's a harsh world out there. And if you don't have machine learning on a grant right now, I don't think it can get accepted. That's my pessimistic view on things at the moment. Yeah, I don't know if anyone else has any comments on this topic or would like to open up to other topics. So this discussion session's running over a little bit. I'm happy to keep it running a little bit more, but we do have a second discussion section at the end of the meeting, and that can run as long as anyone is interested in participating. So we still have plenty of time to have discussions if other topics come to people's minds. So if no one else has any pressing topic of discussion, I'm gonna then move over to the next speaker.